This is a single-phase vector tutorial. We're going to cover some additional information, stuff like some theory and history that should help out with understanding. So this is what a vector diagram looks like. This circle in the bottom left is a vector wheel. In the top left, we have the transformer's nameplate information. Top right is the system voltage, or the phase-to-phase voltage. The lines below it are the primary conductors. The lines down here are the secondary conductors. Below that tells us what voltage the customer needs. The section next to that is where we write in the secondary voltages. And this obviously is a transformer. So the first thing we're going to examine are the numbers that are next to HV on the transformer's nameplate. Ultimately, we're going to cross out the higher number because the one you need to be concerned with is the lower one. However, we should get an understanding of what both of those numbers mean before we move on. Now, there's a lot of confusion surrounding this issue. The reason being is an inconsistency between the design of these exercises and how utilities stock transformers. It's pretty well understood what this first number means. It is the voltage that the primary coil of the transformer is rated for, meaning what voltage it should be hooked up for. However, there are some discrepancies about this second number. Some say that the second number is the system voltage of the circuit the transformer is getting installed to. And typically, that's correct. If you look at these Riverside Public Utility nameplates, this transformer goes on our 12 kV system and is hooked up 6930 phase to neutral. So you see the smaller number there, 6930/12,000. This transformer also goes on our 12 kV system and is hooked up 12 kV phase to phase. Notice it doesn't have that smaller number. Usually that's how it works. A utility will stock transformers that way. The transformers that are hooked up phase to neutral have that lower number and whatever the system voltage is. The transformers that are hooked up phase to phase will only have the system voltage. However, for the sake of these exercises, you'll have to think about it a little differently. Think about it this way. The second number represents the system voltage that you would find the first number in if you measured from phase to neutral. But in this exercise, the system voltage is 4800, and the smaller number is 4800. But that means that we have a primary coil that is rated for 4800 volts. So, we are going to be hooking it up at system voltage phase to phase. If this number read 8300, then we'd hook it up phase to neutral. And this 4800/8300 volt nameplate would be just like that RPU nameplate saying 6930/12,000. The point is, some of these exercises will have you hook the transformer up phase to phase, and the second number will have nothing to do with the exercise. It's not practical how these are designed for that reason, so simply cross out the higher number. Remember, the smaller number is what the coil needs to be given to put out the listed secondary voltage. Hopefully that explains what the second number is about. Now we're going to get back into how to find polarity, and we're going to start off with some standards. The American National Standards Institute, also called ANSI, dictates that any transformer with a primary coil rated greater than 8,660 volts or having a wattage greater than 200 kVA is to be manufactured subtractive. And if both values are less, then the transformer is additive. And this standard was put in place to limit additive transformers to the smaller sizes. This information can be understood a lot easier on a graph. So I've prepared one here. You have voltage on the y-axis, kVA on the x-axis, and these respective benchmarks put in place. They intersect and form that box. You can see that if both values are less, then it will fall in the range of additive, and if either value is higher, then it falls in the infinitely larger subtractive zone. So we'll put it over here in the corner for reference. Now we're going to cross out the higher number like we talked about earlier. And as discussed, the transformer's primary coil is rated for 4,800 volts. The kVA of the transformer is 75. So we'll write this information in on the graph over here. Based on ANSI standards, the transformer is additive. So to reiterate, if either of these values had been greater than the respective reference values on the chart, the transformer would be subtractive. Now we can label the bushings of the transformer. So we'll start off with the primary side. These are always going to be laid out the same with H1 on the left, H2 on the right. And then we'll do the secondary side, and this is a part that can change with respect to what polarity the transformer is. So if it's subtractive, X1 would be on the left as well, and the bushings would read 1, 2, 3, 4 left to right. Conversely, additive is 4, 3, 2, 1 left to right. You can remember this however you want to. The mnemonic I used was 1 minus 1 equals 0. If the ones line up, I have a subtractive equation that equals out to 0. But again, remember it however you want to. Just figure something out that works for you. Now before we continue with vectoring, let's try to get an understanding of what polarity means. We're going to address how the two forms function differently from an electrical standpoint, and give a brief history on how they came to be. And later in a bank tutorial, we will address a topic called displacement and how polarity relates to preferred wiring methods. However, we're not going to cover that in this tutorial. So the differences between additive and subtractive transformers is pretty simple. It all stems from how their primary and secondary coils are wound with respect to one another inside of the transformer. Now the coils can be wound clockwise or counterclockwise around the transformer's core. An additive transformer has its coils wound in opposite directions, and a subtractive transformer has its coils wound in the same direction. But how did they come to be? Well, in the beginning, transformers were wound without respect for polarity. Sometimes they came out additive, other times they came out subtractive. There wasn't a rhyme or reason in their manufacturing. But people started figuring out that was a problem when going to parallel them or use them in banks. If the polarities of the secondary bushings didn't match up, then stuff started blowing up. But that was the process, trial and error, figuring things out. They figured out that transformers of different polarities could work when paralleled or in banks, so long as instantaneous polarities matched up. So alternating current, as you know, is changing polarity 60 times a second. That means that the bushings were alternating between positive and negative. So long as the bushings matched up, then it was all good. So long as when this bushing is negative and this one is negative, everything's okay. But they thought that was dumb, so they started making them all additive for uniformity, which seemed like a good idea at the time. But as transformers got bigger in kVA and voltages got higher, they started seeing problems surface in the additive transformers with regards to the buildup of magnetic flux. You had transformer windings burning up and failing as a result. And this was years after they had made a bunch of them additive. So, the ANSI group made a standard, the same one you saw on the graph earlier, to limit the production of additive transformers to the smaller sizes, since changing them all out would be unreasonable. And that's really all that we need to cover about the history of this. If you want to read more or find where I got this information from, there is a link in the description for the article. Now we're going to get back to wiring up the transformer and move on to the secondaries. So we'll start off with understanding what secondary voltages we have available to us, and you find that information on the nameplate of the transformer. LV 120/240 volts means our transformer has two individual 120 volt coils that may be put in series to produce 240 volts. The next thing that we need to understand is what needs to be supplied. So we'll look at the customer needs section, and there we're going to find two important pieces of information. Explicitly, it tells us what voltage is needed. In this case, the customer needs both 120 and 240 volts. And furthermore, that information implies how we will need to wire the secondary side, internally and externally. The internals are done first, connecting the coils to the bushings. So this process is going to look a little different in other vector diagrams, and that's because there's different transformer constructions in the industry. Sometimes you'll have 4 bushings, sometimes you'll only have 3 secondary bushings. You don't always have 2 independent coils. Sometimes it's 1 long coil with just a mid-coil tap. And in the case of our bird transformers, these coil leads are actually tied into the bushings, and so you design how they're connected with one another externally and not internally, as you would with an overhead transformer. However, the theory isn't going to change. So just wrap your head around the concept of how these coils are being configured with each other using connections. So putting the coils in series is kind of like making 1 long coil. And you'll get 120 volts from either end to the midpoint. You'll get 240 volts from either end of the coil to the other end. Now, another way you could configure them is paralleling the coils, which is also called stacking them together. In effect, this produces 1 short coil that can only produce 120 volts, but at a higher ampacity because essentially the coil is thicker. Obviously, this transformer is supposed to be put in series based on our customer's need of 120 and 240 volts. So now that we have the pod assembled internally and know which bushings are which, we'll start connecting the wires on the transformer and drawing in the vectors as we go. For this project, as we make the physical connections, we'll draw in the vectors to illustrate what they represent and hopefully reinforce the concepts. And we'll begin with the primary side. As explained earlier, during polarity, this transformer is to be hooked up phase to phase based on the circuit voltage and rating of the primary coil. We could use any phase, but we'll go with A. And then we'll show that on the vector wheel. Because this transformer is being connected phase to phase as opposed to phase to neutral, we'll start our vector at 0 degrees. When a transformer's coil is connected phase to neutral, we start the vector at 330 degrees. Now you could actually start this at any degrees on here, but this is how the JATC does it, so we'll just follow suit and keep it uniform. Next, connect the line to H1 and illustrate that on the vector. And the next thing that happens is the coil is energized. Typically this part isn't illustrated, but some guys want you to, and I'll only be doing it for this one to reinforce what a vector diagram represents. So this line on the vector actually represents that coil on the transformer. As far as putting the arrowhead on it, technically that's what makes the line a vector. It has both a force and a direction. But the thing about alternating current is that arrowhead is flipping sides 60 times per second. As such, it's only a momentary representation of direction. Remember what Tesla was saying on the earlier slide about polarity and alternating current. When we draw the arrow in on the secondary coil, you'll see that it's facing the opposite direction in this example. And that's how it works in an additive transformer. That is, the current is flowing in opposite directions across the coils. However, X1 is negative when H1 is negative, and likewise, X1 is positive when H1 is positive. That is why the secondary and primary arrowheads on the vector wheel will still be pointing in the same direction as each other, because we put X1 and H1 coordinating with each other over there. Put simply, where X1 is located on the transformer may change, but regardless, X1 is still the same instantaneous polarity as H1. Again, not everyone cares about the arrows, so most times you probably won't be seeing them. All the same, for this one, you will. Next thing, follow the electricity's path through the primary coil, and you'll see that it connects to H2. We'll write that in. Then connect H2 to a phase. We'll use B. Now we'll illustrate that on the vector. And because this is transformer number 1, obviously, as there is only one in this project, put that 1 mark there on the top of the transformer. We'll label the vector to represent that this coil belongs to transformer number 1. And that concludes the primary work. Now moving on to the secondaries. So in real application, you will not hook up the secondaries in this order. It's only for illustration purposes that we are going out of order. And by now you should know the correct order of operations. That said, we'll begin by connecting X1 to A. And same as the primary vector, the secondary will also begin at 0 degrees. Connecting A to X1. Becoming common with the secondary coil. And the other side of the coil, X4, will connect to B over here at the transformer. Likewise, we'll represent that on the vector wheel. Then we'll install the neutral, and if you notice, it's essentially a mid-coil tap. We'll do the same thing over here by drawing a ground symbol tapping off of the middle of the coil and denoting it as the secondary neutral. Then label your vector to represent that this coil belongs to transformer number 1. And I haven't been asked for these before, but these are the other bushings, X2 and X3, relative to the vector. The last step is voltage readings. The two phases, both A and B, will read 120 volts to neutral. And measured from phase to phase, you'll read 240 volts. And there's no C phase in this scenario, so those values will not be applicable. And that concludes this single phase vector tutorial. Thanks for watching.